Hello everyone, and welcome to Lecture 3. In this lecture, we will be taking our first steps in Magma. Now, I will show you a very simple script written in Magma, and then we will go through each line, step by step, figuring out what it does. Through this, we will understand the basic syntax and functionality of Magma. After that, we will modify this script a little bit, making it slightly more complicated, thereby learning a little bit more about Magma. I recommended in Lecture 1 that you have a text editor with Magma syntax highlighting. So this is what I have at the moment in my computer. So I will be coding in my text editor, and then I will copy-paste what I write there into the browser. As you will see, this will make it easier to debug what I'm writing, because I will be able to see what is a function and what is not, for example. Alright, let's begin. Now we will begin with the following script. The goal is to understand every line of this script, including the most basic operations, such as assignment of value. And the goal would be to be able to write scripts like the one that I'm showing you right now. Before we deconstruct this script, let me show you what it does and explain to you the connection to our previous lecture. I copy-pasted the script from the previous screen, and I'm pasting it here. Now we run, and we get an output of a list of tuples. So what I've done is, in fact, I've computed the points on the circle over the finite field with 17 elements, and the list are the x and y coordinates of the circle. Let's go back to our text editor. So here, I want to talk about the first line for a little bit. Let me delete the rest. So here, the first line is already something very important. What I'm saying is that the letter P should contain the value 17, and the assignment operator for this is the colon followed by the equal sign. And each such command should end with a semicolon. So every mathematical command ends with a semicolon in Magma, and this too is a very important lesson here. Just like pretty much any other language, you can use the letter P, create another mathematical expression, and assign the value back into P. So let's do this now. For example, this expression will evaluate P plus 1, the right-hand side, and then assign the result of this evaluation to the left-hand side. Let's see what the result is. This too is an important lesson. The output is nothing, because when you assign a value to something, then there's nothing to output. If you would like to see the result, then you can type just P, and now we get the result. Since mathematical commands end by the semicolon, I don't need to enter a new line. For example, I could do the following. Now let's continue with the second line of our original script. The second line of our script assigns finite field 17 to F. So we've learned about the assignment. P, of course, equals 17. Therefore, this is clearly what we're doing just by reading the text. In that sense, the user interface for Magma is highly intuitive. So we can still learn something from this second line. If you see a function name from in someone's script, for example, you've seen finite field in my code, and you don't quite know what it does, or perhaps there are variations on it which you would like to find out about, then Magma has help inside the calculator as well as the main documentation. So let me show you how you can learn more about the command finite field. I open up the calculator and simply type question mark the function name that I'm interested in. After I click submit, I see that there are in fact two matches for the function finite field, and it's asking me to choose which one I would like to learn more about. I will choose the second one. I simply added question mark 2 below my first line. Since this is a calculator, it re-evaluates everything from scratch and doesn't remember my previous submission. Therefore, things have to follow one another. In an interactive session, of course, it would have remembered my question mark finite field, and I would have just added question mark 2. Here, we're learning more about this function. For example, I can write, it says here, finite field, prime, and the power of the prime that I would like to consider. You can learn about the first version of this function by just asking question mark 1. And this is a place where you can just input the prime power that you're interested in, and it will generate the finite field with that number of elements. This is where you can begin to appreciate the syntax for the user interface of Magma. It's highly intuitive. It's clear that I'm creating an affine space over the field f just by reading this command. What it says here is that essentially create the vector space f to the power 2. So the plane over the field f. Of course, we will consider it as a geometric object, hence the name affine space. And we will have two coordinate functions. So given a point, I will be able to read its x coordinate and y coordinate, so to speak. And my coordinate functions, I declare them to be x and y. So that's what's happening at the left-hand side of this command. The capital letter A will denote the affine space, and the letters x and y written in these brackets are my coordinate functions. Of course, you can learn a little bit more about the function affine space by using the question mark. But we will continue on and look at the fourth line of this script. So this says f should be assigned the polynomial x squared plus y squared minus 1. Now, since we're doing algebraic geometry, we're welcome to create polynomials using the coordinate functions. And in fact, the space, the affine space, should really be interpreted as a user interface for the polynomial ring in x and y over the field f. The polynomial f defines the circle that we have studied in the previous lecture. And in particular, since my base field is f17, then this is the finite circle in the name we have given to it in the previous lecture. The polynomial f defines the circle. Since I'm working over the finite field f17, then I'm thinking of the finite circle over this field. In the last lecture, we were interested in counting the number of points in these finite circles, and so this is what we're going to do in the next lines. The next line of this script creates essentially the zero set of this polynomial over our finite field. Of course, it's a little bit more sophisticated or, simple in some sense. It really continues to remember only f, and it gives us just a user interface for asking better questions about it. In this case, I've assigned to the letter C my circle. The syntax for this is to say scheme, the ambient space, and the polynomial. You can also input an ideal of polynomials or a sequence of polynomials. But you should remember that this expression scheme should really be treated as a good user interface. As for the last line of this script, I'm asking for the points on C. Once again, I encourage you to ask a Magma calculator or the handbook directly what are the limitations of this command points. But in this case, over finite fields, it works very well. You can also ask questions over other fields, but then there are strong limitations. Now that we've studied the script, let's look at the output once more and then make one small change. Here's the output once again. Now, I just want to point out the first 2 points on the circle. namely where the x-coordinate equals 1 and the y-coordinate equals 0. It's the place where the x-coordinate is -1 mod 17 and the y-coordinate is 0. These two are kind of special points, and then the other points will be duplicated in the x-coordinate with plus and minus y-coordinates. For instance, here I have x equals 0, y equals 1, and then you can find that there's also x equals 0, y equals -1 over here. Now, one small change to this script, I can ask for the number of elements in a set. That's very convenient. That is done by the hashtag symbol before the set or set-like object that we have here. And we see that there are 16 points. That's 17 minus 1, which is the number we would have expected, since clearly -1, that is 16, is a square modulo 17. And we've computed in the last lecture, and this implies the number of points should be 16. So we're on good track. Last week, we could compute the number of points on the circle over a finite field for every prime. Now, we would like to do something at least similar here. So I would like to compute the number of points on the circle for at least a few hundred primes. And for this, I would like to write a for loop where the prime p ranges over many primes. For this, it looks like I should at least know how to generate a list of primes. And I will show you how you could do this if you didn't know where to begin. I go up to the documentation page of Magma, click on Handbook, and here my question is about primes, so that's what I will write. The first entries are about the chapter in the Magma documentation book. The second ones are examples related to primes. And here are a list of functions whose name includes primes. And the first two seem like a good match: primes up to b and primes in interval be. I will use primes up to b. You can learn more about these functions by clicking on the name and reading about it. As you can see, the function will do what we want. Alright, and let's go back to our calculator and see what the output looks like first. There you go. We have the list of the first primes up to 100. Now, I'll show you how you can write a for loop. The prime p equals 17, that goes away. I would like this p to range in the sequence of primes up to 100, let's say. So we know how to generate this sequence. It was done by primes up to command. So I'm saying for p in this list, do, and then there's the script, and then I'm ending this for loop with the command end for. You see that the first line does not need a semicolon at the end, sort of it's just initiating the rest of the mathematical operation, but the final line does, it's concluding a mathematical operation. Now for each prime in this list, the script inside of this for loop will be executed, and the only thing that will be output is the only line where there is no assignment. That's the last line where I'm outputting the list of points in the circle. But that's perhaps too much to see, so I will instead output the number of points. That might not be super instructive when I'm faced with an array of numbers. I also want to be told which is the prime number. So I will say p, comma, and then number of points. That will work. I've executed the script, and the output we see on the screen. So for p equals 2, we get 2, and then 4, 4, 8, 12, 12. This will match the numbers we've computed in the last week. You could want to be a little bit more explicit here. Let's add perhaps description to the numbers that we're outputting. I just need to add strings. And here it's now a little bit more verbose, but this can be useful. Next up, I want to check whether or not these computations are matching my predictions from last week, where we said the result should depend on whether or not -1 is a quadratic residue modulo the prime p. There is a command called is_. I need to input the number -1, but from the field fp. So we will learn how to convert the number -1 from the integers into the number -1 in the finite field. Here, whenever you can convert one object naturally into another object that naturally has the same name, you can use the exclamation mark. That's a coercion operator. So I've coerced the number -1 from the integers into the finite field f17 in this case. And let's give it a name. Let's call it -1. And I would like to ask if this number is a square. This command will work. And before I copy-paste everything into the calculator, notice that the first line is shaded, and I've written things in words there. That, of course, is the command operation. You can start a command anywhere with 2 forward slashes, like this. Of course, any commands will be ignored by the kernel. The calculator outputs true and the number 4. So the function is_, sometimes outputs two things. One of them is the answer to our question, which is whether or not the thing that we entered is a square in the appropriate field. And the second thing is the square root. So the square root of -1 is 4 in f17. Of course, I don't have to assign the -1 coerced to the field to a variable first and then plug it in. I can just write it into the function. So is_, f coerce -1 will work just as well. This time it gave another square root. Of course, there are two square roots, 4 and -4, and that's 13. Let's modify our script so that we can check what you might know already, that is -1 is a square in the finite field fp, if and only if p is 1 mod 4 and p is greater than 2. So I've created a loop which will tell me whether or not p has -1 as a square root, and I also want to check if p is 1 mod 4. So let's see what this returns. The calculator returns the following. The first two entries, in case there are 3 entries, are coming from the function is_, and we see that there is a square root exactly when p is 1 mod 4 or when p equals 2 by inspection. Let's do this search slightly more sophisticated by adding an if conditional. Now I've saved the output of is square. An important distinction here is that if you say assign the output of a function to something, then it will assign only the first output of that function. And I'm going to store in p mod 4 the value of p modulo 4. I modified the script so that I have a conditional behavior here. I've added this if command. So if something happens, then I'm going to execute the small script in between if and if. So here I'm saying that if this expression here is true, then you should print this is odd, and then the prime p. And then we end this if clause. In between if and if, I can put an arbitrarily long script in principle. Note that I start with if on the first line, then put then, and then I end with and if. Now it reads very much like mathematics. If minus 1 is a square and p mod 4 is not 1. So this ne means not equal to. Therefore I have two booleans here. One checks whether or not p mod 4 equals 1, and the boolean from before, the square. Let's see what this does. And the calculator returns the oddest prime 2. We can of course increase our search range. Let's go and search for the first 1000 primes. And we get the same kind of answer. Of course, this is very easy to check by hand. Now let's go back and confirm our expectations from the last week as to the number of points on the circle using what we've just learned. On the screen, you will see the two scripts that we have written so far. Now we're going to modify the first one to phrase our expectation, which was that if minus 1 was a square modulo p, then we expected p minus 1 points and p plus 1 otherwise. So let's make sure that the computer can phrase our expectation, and then let's compare the expectation against the point count that the computer is doing in the first script. I've typed the script. What we have learned from before was the conditional if and the function is square. So if minus 1 is a square, then my expectation was that the number of points should be p minus 1. And here's something new. We can also use the else command. So if the condition inside the if clause fails, that is minus 1 is not a square, then our expectation should be p plus 1. And I end the if clause, and I'm simply outputting the number of points on the circle as computed by Magma, our expectation, and the prime p to remind us what we're doing. As you can see, our expectation fails only when p equals 2. We have realized that this was already an exceptional case, also in the last lecture. And otherwise, as far as we can see, our expectation matches what the computer computes. Of course, I don't want to check this with my eyes if I were to have thousands of primes. So let's increase the size of our loop, and then let's just warn us if the expectation does not match the reality. I've modified the script so that I'm not outputting anything unless there is something that's happening beyond my expectations. And now we know that the only strange prime is 2. Let's increase the range of our search. So that will means changing the first entry here. Let's search for the first 1000 primes. And again, we find no exceptions. I repeated this calculation for the primes up to 10,000, and it took me 8 seconds, and the output is well expected. Let's do one more thing. Let's include one command where when p is 2, then we skip this case. I've added these 3 lines of code. So if p is 2 and the equality is checked by eq, then I'm saying continue. This means skip this particular instance of the for loop, and then we move on to the next value of p. Since there is no output if I do this, let me add one more line just to tell me if the code is completed. And we get the expected answer that there are no failures of our expectation within this range. That's it for the introduction to Magma. There is of course many more things to learn. In particular, I have not covered sequences in depth, but this is a good starting point. I would like to encourage you to read the first steps PDF in the documentation. That's here in documentation. You go to first steps in Magma. I've mentioned this document in the first lecture, and it's a very quick read. It's very well written, so I suggest you go through it and play with it. That's it for today. These were our very first steps in Magma, and from now on we're going to pick up pace and do more elaborate constructions in the next weeks. As for Wednesday, we're going to continue with a more theoretical lecture on Grassmannians. See you then.